Alison is going to tell us about uncertainties. I need to introduce you just really quickly. Alison is a professor at the University of Newfoundland, and she's also part of the SPIN advisory board. So she's keeping an eye on how well we're doing.
Something like that.
Something like that. So please go ahead.
Awesome. Thanks, Celine. So I'm really excited to be here. And I thought I'd start. I'm always asked, where is Newfoundland? And so I thought I'd start by telling you that. So Newfoundland is the easternmost part of Canada, and St. John's is the easternmost city. So it is directly across the Atlantic, basically from Ireland. And I like to tell people also that we hear about Newfoundland as the place that settlers first came from Europe to North America, but of course it has its own history from far beyond that. And Newfoundland is actually the ancestral home of the Beothuk, who are an extinct Aboriginal tribe. Thank you to the first settlers who came to Newfoundland for that accomplishment, I suppose. So that's where I'm from, and I'm really excited to be here. I am on the SPIN advisory board, but this is the first time I've got to come and meet you folks because of many COVID adventures and how Newfoundland chose to deal with that. So this is my first time outside of Canada since 2019. So I'm super excited to be here. So, and this is, I'll just do it this way. So I'm going to start talking about uncertainties, and I'm going to talk about, let's see if I can do this the way that Andreas did it, make it go away. There, okay, perfect. So I'm going to start with a fairly simple example, and it's a gravity inversion example. And I'm going to start with this example because it's quite simple, but I think it gives us the opportunity to illustrate a number of concepts with a pretty straightforward problem. The other reason I'm sure that I thought about gravity is I just taught gravity to my undergrads, so my brain is thinking about gravity. But for those of you who maybe come from physics and have only experienced geophysics through seismology, I'll just quickly give you an overview of how we measure gravity data and what we use gravity data for. So as you've certainly heard, gravity is a force that holds us on Earth. And if we measure gravity very carefully, we can use it to understand variations in density. And it's a very simple problem to calculate what we call the gravitational anomaly, or how gravity differs from what we expect, based on just the density of the subsurface. So you can do this just by adding up little volumes with changes in density. And in particular, for many simple shapes, you can do this in closed form. So you can just do the integration without even needing your numerics, and you can get a nice little formula for the gravitational anomaly that you would measure if you have a spherical body. So you can do a number of different shapes. I suppose if you have the patience, you can probably do many, many different shapes. But the most common ones that we would tend to look at are spheres, which simulate, like ore deposits is one very common thing we would use for spheres, or underground caverns. This is more common, I would say, in near-surface sort of applications, but it's a very straightforward calculation to deal with. So I'm going to talk about uncertainties, not really gravity data, but I'm going to show you two examples of gravity data where I've added some noise. So this is simulated data. And this is kind of, the spherical anomaly is what you see here. It's this kind of Gaussian bell curve sort of shape. And you can see I've added noise, okay? And I think that all of us can look at this and we have a kind of general idea of what the underlying model is, okay? And we can see the scatter in our data. And I've added scatter to our data in two ways, okay? And you can see two different data sets that I might collect. But of course, typically in geophysics, we have a single data set, okay? Just to give you an idea, I think this is 500 data points. It takes my class of undergraduates 90 minutes to collect 6 data points. Now, they are very slow because they're beginners, right? But nobody is going to go out and collect your 500 gravity data points 100 times so that you can understand the statistics of the measurements. You typically get one data set from which you're going to attempt to estimate the uncertainties. And I'm going to talk a little bit about how we do that and a little bit about how we use those uncertainties. But let's start with just our objective function and where these two different data sets come from within that objective function. So in this case, I've actually perturbed the model. And that's how I've managed to perturb the data, so that it looks like that. Whereas in this case, I've actually just added noise to the data. Okay? And now, as Andreas said earlier, in both cases I've done this in a Gaussian way, because it's easiest. Okay? And most of what I talk about is going to be strictly true in the Gaussian case. Okay? But we use it and we extend it in a lot of different ways, but most of the sort of theorem aspects are done for a Gaussian, because it's easier. Okay, but now we need to know, if we want to just evaluate our objective function, we should know the covariance of our noise and the covariance of our model before we even get started. But I just told you that typically what you get is these 500 data points. So we have a bit of a problem. What are we going to do? How are we going to get these uncertainties when we have one set of data and we don't actually necessarily know what might be causing the scatter that is certainly going to be in our data set? Okay? So I'm going to talk a little bit about covariance matrices, remind you of the definition. I'm going to talk, and then I'm going to start talking about these two sets of uncertainties. So we'll talk about data uncertainties and model uncertainties. And then I will talk about how we take those data uncertainties and move them into the posterior so that we get an estimate of the errors in our final model. Okay? And like Andreas said this morning, right, this is a 1-hour talk on uncertainties. You could probably teach an entire course on uncertainties if you wanted to. So my goal is to mostly give you some things to think about and some possibilities to try when you think about your own problems. Okay? And I'm not going to give you a whole bunch of sort of details about sort of the underlying pieces. My goal is really to give you kind of an overview so that you know what you have to look for your own problem. Okay? Because these things also change problem to problem. And of course, I bring my own biases from the problems that I've worked on when I think about what I need to tell you about uncertainties. Okay, so what is a covariance matrix anyway? So this is the definition of the covariance matrix. And if you forget what an expectation is, you can basically assume that it's the mean. Okay? And if you look at the covariance, or what the covariance is describing, you have your data point minus your mean. Okay? And then you square it if I is equal to j. So this hopefully starts to sound like a standard deviation to you. Okay? And in fact, on the diagonal of our covariance matrix is the standard deviation. Okay? So what about the off diagonal? Well, this is how okay? But we have to start with some idea of how to get a single estimate of the data covariance, or the model covariance, or the posterior covariance. Okay? So we're going to start from the data. Okay? And in the data, you can put a lot of different things into those uncertainties. my data have changed. Okay, I'm getting a slightly different measurement. Okay, we can think of that as measurement uncertainties. Okay, and if I have 10 different people collect the data, I may get 10 different levels of measurement uncertainties. Okay, we can introduce uncertainties in our data by using different types of processing methods. Some types of processing methods will couple different data points, okay? And that may start to introduce correlations in your data that may not even be there when you first collect your data, okay? And so that's another aspect to think about. We also have to think about how the uncertainties in our recorded data are going to be changed by everything that we do to our data between when we record it and when we start doing our inverse problem. So if we sort of split our process into data collection, data processing, and then inverse problem, we want to think about how the uncertainties move from place to place. Because in the end, we're typically trying to answer some sort of question about the Earth, and that question about the Earth we would like to answer with some form of an error bar. Okay? And so we really want to understand how all of these things move through the system, okay? And now, I'm mostly talking about uncertainties, and I often will use the word error, and I think you hear that also used quite a lot colloquially. To me, when I sort of try to be careful, I would say that an error is something that you identify that you did wrong, and you need to fix it, like you need to recollect the data, okay? So if we talk about the gravity problem, gravimeters are super sensitive instruments. If you drop it, you need to start again, okay? This is not an uncertainty, this is a screw up. And so then we need to go back and just do the whole thing again, and we're not going to account for that in our inverse problem. We're going to recollect our data, okay? And it's important to think about that when you're collecting your data and when you're processing your data. Because if you're thinking you have to put such a big error bar on your data, maybe the best thing that you can do to recover a more useful model is to go back and recollect the data, okay? And I think you have to keep that possibility in mind as you think about your data uncertainties, okay? But so in our gravity example, when I added noise to the data, okay, I just calculated the gravitational response of my big sphere, and then I added random noise, okay? That's a sort of standard way to produce noisy data, and it clearly goes in the data covariance, okay? And in this case, I did it 100 times, and then I can generate an error bar, okay? That's the perfect situation. But this is numerical data, and it's also a very, very simple forward model. So I generate 100 realizations faster than I get bored. I just hit enter and it's there, okay? In this case, what I did is I put a whole bunch of little spheres in the near surface. So I'm simulating something that is essentially sub-resolution, okay? So you're not seeing in the data that, there's a little tiny Gaussian from this little sphere here. What you're seeing is just a fluctuation in your data, okay? That goes in the model covariance, okay? And once again, I can do this super quickly, so I did it 500 times, and here we have the results on your gravity data of you changing the near surface. But typically, again, we have one realization. We're going to have to try and figure out where we put these errors in our data and how we're going to use them as we go through our whole inverse problem. Okay? And I'll talk a little bit more about this, and that's sort of what I'm going to talk about primarily over the next 45 minutes or something. Okay, so in this case, I sort of pre-cooked this so that I get a very similar distribution from these two different possibilities. Okay? And it's not hard to do that in this case. Okay? But I've got complete overlap. So if I've only collected a single data set, the bottom line is I do not know. Right? I have created a problem with a beautiful null space. Okay? There's two equally valid ways for me to generate data with this kind of oscillations in it, okay? So when you look at your data and think, okay, my data is noisy, that goes in my data covariance matrix, you should think about whether all of that noise actually belongs in your data covariance matrix, or if some of it belongs elsewhere in your inverse problem, like in this case, in the model covariance. All right. Now, how are we going to estimate these uncertainties from our single data set? So, like I said, we're not going to go out and collect our data 500 times. Maybe if it's a lab experiment, you might do it 5 or 6 times. That's probably still not enough to get a particularly good estimate of the standard deviation, okay? But there's a bunch of things that we can do. They're somewhat ad hoc, but that doesn't mean that they're not useful, okay? So one thing that is common, and I would say this is quite common in seismic, is to look at your data before your P wave arrives, okay? So the analog of this here in the gravity case would be to look at my data down here before I really get into the anomaly. How much do your data fluctuate there before you started to see a signal, okay? So in this case, I said, well, I'll just fit that to a line, okay, and I'll calculate a standard deviation. Now, it works fine, and it gives me a number, but you can see it's about half the true standard deviation, okay? And so what's commonly done in this case, actually, if you're estimating the standard deviation this way, is to multiply this estimated standard deviation by some factor, and say then you're trying to be conservative. You're trying to make your data errors as big as is reasonable, so that your model errors in the end will also be as big as is reasonable, okay? So that's one possibility. You can also smooth the data and use the mean, so that works reasonably well in this case. Okay, so in this case, I just applied a smoothing filter, and then I get the blue data, and then I just take the standard deviation around that mean. Okay, and that gives me a slightly different standard deviation. It's actually quite close to the true standard deviation in this case. Okay, and there's a lot of reasons why that's quite close. I have quite a few data points. Okay. Smoothing it is actually more or less correct in this case as well, right? I'm expecting smooth data and so forth, okay? So those are kind of two very standard ways to do this. A couple of other ways that you can do this is to repeat a few measurements if you can. You know, you don't necessarily need to repeat every single measurement, but maybe you can find a few points in your data where, like the data that Andreas showed this morning from the nuclear explosions, where you have a higher degree of repeatability than normal, and compare those to estimate your standard deviations. There's a nice, really recent paper where they actually used reciprocity. So it's an exploration, well, it's not really, it's kind of a mid-scale example. And they basically said, our data should be reciprocal. I should be able to interchange the source and receiver and get the same data. And so the amount that the data violate reciprocity is an estimate of the error, okay? And now, it's an estimate of the error. It's hard to really quantify whether that is exactly the error. So this is a situation where you're always guessing to a certain extent, okay? And you know, I think that Thomas may talk about how to do these things in a little bit of a more robust way. But a lot of the way we estimate these has some element of guesswork in it, okay? And then this is just talking about estimating a single standard deviation for my whole data set, okay? In an ideal world, I would like a single standard deviation for each point, and then to measure how errors in one data point affect errors in the next data point, which are the off-diagonal elements of our covariance matrix, okay? Estimating that whole matrix is a challenge, and you have to really ask yourself, how big an error do you really expect? You know, if I go make a gravity error here, or gravity measurement here, it has a certain uncertainty. If I then step to the next location and make another measurement, I don't necessarily expect the uncertainties to be correlated, okay? The errors, you know, the student forgot to level the machine, okay? Those may be correlated. Okay, all the data from student number 1 is terrible, okay? But those are more in the category of screw-ups. The solution to that is send student number 2 to recollect the data and remind them that they should level the instrument, okay? So I don't see a lot of work thinking about correlations between data points because we do tend to think of these things being independent, okay? This is when we are assuming random noise, okay? When we think about noise as, you know, just parts of the signal that our theory does not account for, then you're going to have more correlations between different data points, okay? And examples of that would be, you know, if you're only inverting for a p-wave velocity model, you may consider shear waves to be noise, okay? In exploration seismic, things are almost always done with just primaries, waves that reflect once. Waves that reflect multiple times are coherent noise, okay? They're going to be strongly correlated from station to station, okay? But you also want to ask yourself then, is the right way to deal with that putting it in my data covariance? Or is the right way to deal with that using a good filter before I start solving my inverse problem and trying to remove those things, okay? And so this is where I think there's kind of more thinking and perhaps more of the art of inverse problems comes in, is trying to understand how to put these different pieces together to give you a good estimate of the uncertainties in your final model parameters. Okay, questions so far? All right. Okay, so now we're going to talk about model uncertainties. So again, we have a bunch of questions to think about, and we have some options. Some things belong in our model covariance, some things belong in our prior, and some things are choices. And in a lot of cases, there's not right choices and wrong choices, but there are implications to your choices, okay? And so we want to understand, if you put something in your model covariance, how is that affecting your recovered models? Versus if you put it in your prior, how is that affecting your a posteriori models that you estimate from your inverse problem, okay? And so there's many different things that can contribute to this. So how much anisotropy are you allowing for? Are you putting that in your prior, or are you putting that in your model covariance? How much do you actually know beforehand? So we talked about velocity ranges. You know, temperature maybe is going to be positive. Density certainly should be positive. You can also generate model uncertainties by having different model resolutions. Okay, so when the gravity example that I've been showing you, I'm putting perturbations in the model that are sub-resolution. Okay, and because they're sub-resolution, and I kind of know they're sub-resolution, it's quite natural to put those in the model covariance. Okay, the fact that density is always going to be positive is much easier to incorporate if I put it in the prior. Okay, because my prior is the distribution I'm starting from when I choose samples. Okay, if I use the Monte Carlo techniques that Andreas was talking about, okay, that's quite straightforward. Only look at positive densities. Okay, whereas trying to put that into the model covariance is a little bit more difficult. Okay, all right. So here's an example. Now, I really like this example for many reasons. But I think it's one of the most thorough papers. This is a paper by Wences Guevara and John Scales from the late 90s, where they really try to go through and do the kind of Tarantola formulation, estimate all their data covariances, all their model covariances, put the whole thing together, and then estimate the a posteriori uncertainties in their final model. Okay, and I'm going to show you this example, and I'll talk a little bit more about this paper again. Okay. But so the way that they went about estimating this model covariance, so I should tell you, they're doing a combination of a kind of, let's call it a sort of straightforward, full waveform-ish inversion, and they're using well logs as the prior information, okay? And so the well log is measuring the seismic velocity down a borehole as a function of depth. And so they took that well log data, and they took a running average of that well log data, which you can probably not see super well, as this kind of gray line that goes through. And then they measured the standard deviation about that mean model. okay? And that is how they got their model covariance. So they basically used complementary data to get an estimate of how much their model deviates from that kind of prior information, okay? And now, like anything, like you can poke holes in this if you want to. There's a lot of assumptions that go into how you're going to compare borehole data to seismic data and so forth, okay? But it is a way of estimating the model covariance. So they're taking information that they have and they're using it to calculate the statistical quantity to fill in at least the diagonal of their model covariance, okay? So we can do this here for the gravity example, and we can do it in a number of different ways. And again, I'm not advocating one choice over another. They're just different choices for how you could try and characterize this kind of uncertainty in your model. Okay, so what I did is I calculated the standard deviation by adding up the density times the volume, okay, because that's our relevant quantity here. And then I divided it by different areas, okay? So if I just divide by the volumes of the spheres, so I just say, you know, I've only perturbed these elements, so those are my background levels, then I get 1,500 kilograms per meter cubed, which is pretty huge, okay, for a gravity perturbation. If I just average within the blue box, then I get about 6, about 7, okay? And if I average in the, oh, pardon me, I got those backward. The orange box gives us 7, the blue box gives us 0.7, okay? So the real point is vastly different numbers based on choices that I've made about which parts of my model I'm going to include, okay? If I kind of do it properly, okay, which is to take my model, so here's, I just zoomed in on this little red box of the model, okay? And you can see 5 different models in my model set, okay? And now I've calculated the covariance across all of my models, and so that's what you see here, okay? But this is actually the diagonal of the covariance matrix, okay? And it's just like when I took my data and I put an error bar on it, okay? And so if I think about calculating the whole covariance matrix for my model, the diagonal by itself is another model, okay? And then every off diagonal, I've got more and more models. So this matrix is going to be huge, okay? It's number of model points by number of model points. Exactly the same size as the Hessian in linear inversion, okay? So even if I can calculate a very detailed version of the model covariance, I might not want to and I might not be able to store it, okay? So again, we have to make some sort of compromise to get to the point where we have a tractable problem. Okay? Now, just to kind of wrap up this part a little bit, I'm going to walk you through this paper by Wences and John. I'm not very good with his last name. Gueva, I think, and Scales, where they're combining well-log data and seismic data. And they're very careful about going through all the different possible sources of error in their data, okay? So they look at random noise, and they get their random noise by looking at data before the first arrival, okay? They look for near-surface heterogeneities, okay? Kind of like what we just simulated, okay? And in that case, they do it by modeling. They model many different possibilities of near-surface heterogeneity, and they look at how that changes the data. Now, there's where you have to be a little bit careful. What is a reasonable range of scenarios to test? And it, you know, it really depends on the situation, and I don't think there's a single answer to that, okay? But if you're going to be thorough, you should check these kinds of things, okay? They thought about modeling errors, okay? So in particular, if there's a problem with the discretization, especially as you try many different models, you maybe keep the same discretization. Okay, so they did that. They modeled with a bunch of different discretizations, and they looked at how that affected their data. Okay, and then they looked at a scaling factor as well to match between the field and synthetic data. Okay, and again, they just tried a bunch of different factors, and they basically went through to average based on those different factors, okay? And once they had these 4 different parts, they then added them together, okay? Now, when you add them together like that, you're assuming that everything is Gaussian, okay? And we do a lot of assuming that everything is Gaussian, sometimes explicitly and sometimes implicitly, okay? And as Andrea said this morning, we usually do it for convenience, okay? And because we may not have the ability to estimate something more detailed than a Gaussian, okay? And if that is the case, then you're probably best off sticking with a Gaussian. Okay, so that's uncertainties and sort of estimating those uncertainties. And now we're going to start moving into what we're going to do with these uncertainties and how we're going to use them in our inverse problem, okay? So I want you to think about this in your head, that you've gone out and you've collected these data, and this is a big part of the reason why I decided I was going to show you this with gravity data. So I've gone out and I've collected the data, and now I'm going to solve the inverse problem, okay? So I'm going to try and fit these data by adding density perturbations to my subsurface model, okay? Do you want to add all these little spheres and fit your data perfectly? Hopefully you're all thinking in your head, no. Of course I do not want to put in all those little tiny data, all those little tiny spheres, and fit my data perfectly, okay? But gravity inversion is a great example because you can. You can fit the data absolutely perfectly by just putting in enough little teeny tiny spheres right at the surface, okay? And many of the earliest gravity inversions did that before they started introducing some regularization to force the inverse problem to put more of the structure deeper, okay? So gravity inversion just didn't work because everything would sit at the near surface, okay? So you 100% can, but you typically don't want to, okay? But then, how accurately do I want to fit my data? Is any model that fits my data within error equally adequate? What am I going to do? So there are a couple of different answers, because I don't think you guys are going to answer me now. It takes like at least a couple weeks before I typically get students to answer my questions in class, so I'm not going to bug you. If I do get answers, I'm going to get them answers I don't want from people who have more knowledge about it than I do. So we're going to start by talking about something called the chi-squared test, okay? So if we start with our usual objective function, we want to minimize this, okay? But I don't want to drive this objective function all the way to 0. Because I know that if I drive this objective function all the way to 0, my model is going to have all these little tiny spheres in it that I'm not interested in, okay? So I want to fit it okay, but not super, super well, right? Because also, like, I don't want to miss by a mile, right? Or by 10 kilometers, but I would like to get close, but not too close. And the way we measure this is something called the chi-squared test. And let me kind of walk you through this with a very simple toy problem. So think about just sampling a distribution. For example, if I'm rolling dice, okay? So I tell you I have a perfectly normal dice. Now you think in your head what that distribution is going to be if I just roll that dice. And your expectation is that it should be completely flat, right? Okay, 1, 2, 3, 4, 5, 6, all equal numbers, okay? But now, what if I roll the dice 6 times? Do you expect 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6? Absolutely not, right? You expect that if I roll the dice 1,000 times, or 6,000 times to make the math easy, then I should have 1,000 ones about, and 1,000 twos, and so forth, okay? But you don't expect to get a perfect match to the distribution with just a very few samples, okay? But the more samples you get, the closer you expect to get to your true distribution, okay? And so that's what this measures here. So this is my true distribution, H, and this is the number of points that are in, oh, okay, backward. This is the number of points that are in a particular bin, so the number of ones. P, that's the probability of getting a 1, and N, that's the number of times I rolled, to my actual distribution. Okay? And if I do this enough times, this should be n, the number of times I rolled, times the standard deviation of the distribution. Okay? Basically, if I tell you that I rolled the dice 6,000 times and I got 1,010 twos, you're all going to go, yeah, sounds about right. Okay? But if I told you that I rolled the dice 6,000 times and I got 4,000 twos, you're not going to trust my dice. Right? Nobody is going to play a game with me with my dice that I rolled 6,000 times and got 4,000 twos. Okay? That's not what we expect. Okay? And so if we think about it this way, this is the measured data spread divided by the predicted data spread. We expect that to be about 1. Okay? And so this is the normalized chi-squared. We've divided by our number of degrees of freedom. I should probably have it divided by n on this side too. Okay? And we expect that to be about 1. So that's the chi-squared test, and it's a very common way of estimating whether we fit our data correctly given the amount of noise that's in our data, especially if you're using a linear optimization technique as opposed to a sampling technique. Okay? Make sense? Okay, so here's an example. So these are just samples drawn from a normal distribution, okay? And you can see that if I draw the samples from the correct distribution, my chi-squared test is about 1, okay? And it's about 1. This is statistics. Nothing is going to give you, 1.00000, okay? It's about 1. Now I'm drawing the data from a different distribution that I'm evaluating against, and I get a chi-squared of 20. That is not about 1, okay? And so this is what we're basically trying to do is see if our data if our model data are statistically consistent with our field data, okay? And it's a very commonly used, very powerful method, I would say, of kind of understanding how to use your data uncertainties to stop your inversion problem at the right point. All right. So far, we've talked about our prior uncertainties and splitting them into a model uncertainties and data uncertainties, about how we estimate these, okay, and how we sort of fit our data imperfectly, okay? But we haven't really solved our inverse problem yet or started to talk about what our error estimates on our final model are going to be, okay? And that is what we are typically interested in, right? Is, I've collected data. What can I say about the Earth based on these collected data? So that's where we're going to now. And so this is where we come into Bayes' theorem, which again, you saw this morning. And we are going to mostly use just the numerator again. We're leaving the denominator completely up to you, Thomas. And we're going to just talk about how do I now think about the covariances and the error and the uncertainties over here in my final model. Okay? So we've talked about a little bit about the prior. Okay? And we've talked a lot about the likelihood and how we're going to put these covariances into our likelihood. Okay? And now we're going to talk about how they come into our posterior. Okay? So let's think about our Monte Carlo simulations that you guys have been working on. So in Monte Carlo, or Metropolis Hastings, it doesn't really matter. This is sort of illustrated for Metropolis Hastings, but it doesn't really matter which one you start with. You start from some prior distribution. Okay, so this is my densities are positive. So there is no point in testing a model where densities are negative. Okay, because we know that doesn't really happen. Okay, and what we're trying to do is estimate our posterior distribution. And I just realized my posterior distribution's covariance moved. But anyway, so what we get at the end is an estimate of our posterior. And when we start to display that estimate and analyze that estimate, we want to get a sense for how fat that distribution is, right? Because if it's a very sort of wide distribution, then that tells us our data don't really constrain that parameter. Okay? And if we get a very narrow distribution, that tells us that that parameter is well constrained. Okay? Neither tell us anything about the accuracy of that parameter. Okay? They're just telling us how well constrained it is. But we would like to estimate that because that's kind of, again, that's giving us the bounds on what we're trying to understand about the Earth and what we're trying to tell other people about the Earth. Okay? Now, when we start trying to go from these prior uncertainties, so that's our data uncertainties, our model covariances, and so forth, to our posterior uncertainties, we have a couple of different paths. So if we think about linear optimization, or kind of gradient descent type thing, then we can write our posterior covariance like this. Okay? And now, it's in Tarantola's book, this derivation, but I'm not going to derive it, but I am going to show you it, also because I think you guys can just do it. Ah, that was not what I anticipated happening when I did that. There we go. Okay, but so let's just, and also because Andreas hasn't gotten to linear inverse problems, so I'm going to kind of very quickly talk about the important part for me of this kind of optimization for solving an inverse problem. So what we do in this kind of linear optimization is we pick a model. And we say, okay, I'm going to start here. This is my objective function. Okay, so this is my chi-squared. And this is a model parameter, whatever you want it to be. Okay, so I pick a model. And I'll pick a model up here because I think it's easier to see in the back. And I calculate the gradient of the function. And I take a step. Okay, calculate the gradient and keep going. Okay, now of course, when I calculate the gradient, what I'm doing is I'm making a linear approximation of this function. Okay, I don't need to stop at linear. Okay, there's no rules. I can make a quadratic approximation. I could make a quartic approximation if I was in the mood. Okay, but if you make a quadratic approximation of the objective function, then what you're doing is you're fitting this objective function to a parabola. Okay, and we sometimes do that to try and step to the bottom of the parabola because it's kind of a quick way of trying to descend. But when we do that, what we're actually estimating is the Hessian. Okay, and in multiple dimensions, the size of the Hessian is the number of model parameters by the number of model parameters. Okay, so this is like the model covariance we were talking about before. Okay, also known as a very, very large. Okay, but it is directly related to our posterior covariance. Okay, and as a result, if we estimate the Hessian, and we know something about our prior covariances, then we can estimate this posterior covariance. Okay? But you have to think about what you are actually estimating. And in this case, what you're estimating is the width of this hyperbola, or parabola. Okay? And so that might be what you want. You want to know what range of model parameters within the basin of attraction that you're in fits your data. That's what that is telling you. It's not telling you that there is another local minimum that may fit your data reasonably well. It's only telling you about the width of this particular local minimum. Okay? Again, maybe that's what you're going for. If it is, then this is a perfectly legitimate way to estimate the uncertainties in your final model. But you should do it with the understanding that that's what you're estimating. Okay. So there you go. We have this a posteriori covariance, whether we get it from some kind of sampling method or whether we get it from some sort of Hessian estimation method. Am I done? Do we get to all have dinner? Probably not, or I wouldn't be asking, right? Okay? But we have a number of other things to think about. So the one that I think about the most is the null space. But we also think about, did I estimate the full covariance matrix? The answer is typically no, okay? Because we just talked about this thing is very large. We estimated the part of it that we were interested in, okay? And how accurately we estimated it and what part we're interested in are questions you want to ask yourself as you set up your inverse problem, ideally, and not only as you're interpreting the final result, okay? And how do I kind of take this covariance and use it to answer my original questions, okay? So for this, I'm going to first kind of walk you through the gravity case and talk about the null space a little bit, and then I'll show you some other examples before we give it up. So let's start by talking about what is the null space of our problem. Okay, because maybe the last time you heard about a null space was linear algebra class, and according to my husband who teaches linear algebra, maybe you didn't learn it very well that time. The null space is essentially unresolvable model differences. So in this case, I have two spheres, and again, this is what I really love about gravity data, is I have two spheres that generate exactly the same data. I can write my null space in closed form, okay? So anytime the radius cubed times the density is constant, I get exactly the same gravity anomaly, okay? So what do I do? How do I characterize that null space, okay? So in this case, if I'm using a sampling method, I should sample part of the null space, okay? Provided I sample that part of model space, it should give reasonable likelihoods in some cases, okay? Now, when you do this, you want to remember that how completely you sample the null space will be at least related to how well you sample the rest of the space, okay? And everything you read about these kinds of methods is true statistically in the if I take enough samples, okay? And Andreas talked a little bit about how do I know I've taken enough samples, but you want to at least ask that question if you want to say that you're sampling the null space or that you're not sampling the null space, okay? If we look at this case, as I already kind of let the cat out of the bag on this one, we haven't sampled the null space, okay? We've only looked at how wide our particular basin is in our objective function, okay? All right, so did I estimate the full covariance? Again, no, you didn't. You almost certainly picked some part of it. And I think there's a lot that you can do by choosing carefully what part of that covariance matrix you want to estimate, and then estimating it in a way that answers the questions you originally wanted to ask, okay? And this ties into what Andrew will tell you in a couple of days when he talks about both variational inference and experimental design, is really thinking about what do I want to answer and how do I use the data I have to answer those questions, which of those questions can my data actually answer, and which of those questions can my data not actually answer. And so I'm going to show you a few examples for this, and then we will leave it for the day. So my first example comes from 4D seismic, and so I just thought I'd tell you very quickly what 4D seismic are. So this is a pretty common technique used in exploration, where you collect field data and then you perturb your model. You collect field data and you make an image, okay? And then you inject something. Typically, well, you either inject or you extract, but in this case, we're going to inject. So you might inject CO2, and you want to know where it ended up, okay? Then you go back and repeat your experiment. And there's two advantages to this from a sort of statistical inverse problems point of view. The first is at least you have two data sets, okay? And the second is you're only typically interested in a small part of the model. So it makes your whole problem much more tractable because your questions are all about a very small subregion of the Earth instead of being about the whole area, okay? So here's an example. This is the true 4D change that we put in. It's a toy example. And what we're interested in estimating is the vertical extent of this anomaly and its horizontal spread, okay, as well as the average velocity perturbation. And here I'm showing you two different potential parameterizations of our model. Okay, so this comes back to thinking about your discretization, how your discretization affects your final results. Okay, so what we can see here, so what you see in the background is the result of one chain of MCMC, okay, and on top is other chains. That's how we're checking for convergence. And we're comparing 12 degrees of freedom to 20. And the true result is the green bar. Okay? So, if we think about, do we need 20 degrees of freedom? Or are we good enough with 12? It depends on the question we want to answer. If all we want to know is how far has the CO2 spread from the wellbore, maybe we're content with just under the mean is within our distribution. Okay? Maybe that's enough. If we want to estimate the average velocity, probably it's not. We probably need to use the 20 degree of freedom model to be able to answer the question, is my average, what is the average velocity? Okay? There's also situations where the noise doesn't really matter, and the initial conditions don't really matter. So here what we're changing is actually the background model. The model we do all the way propagation is outside of our little small domain. Okay? And what we can see is we use a bunch of different models, and they all give us about the same answer. Okay? It's a little narrower if we use the true model. But even with high noise, we get relatively similar results, whichever model we use. So it doesn't matter. Okay? If what we're trying to answer, the question we're trying to answer is, what is the kind of basic range of our change in velocity, maybe it doesn't matter what that initial model is. So then I can go back and say, okay, I can use a rougher estimate. I don't need all of the detail to get the answer that I want. Okay, here's an example where we did the same sort of thing with a field data set. This is from offshore Newfoundland. And here we have kind of a mixed answer. Okay, if we want to understand the velocity change, we're good. We've constrained that to within sort of 6 meters per second, which is really good. We're totally happy with that. The fault block area, though, we've kind of constrained to within 1,500 meters. Could probably have done that without the data. Okay. And so then we say, okay, well, what questions do you want to answer? If you want to answer the fault block question, then we need more data, and we need to do a more detailed calculation. Okay? If all I want to know is the velocity change, I'm done. I can go home. Okay? So here's another example. Okay, this is kind of along the same lines as the one that I just showed you, where what we're trying to do is understand how this background velocity affects where we image the anticline that you see in black. And now, one way that we can display this kind of uncertainty is to essentially play a movie of all of these samples, okay? And that was suggested maybe by Tarantola, but quite some time ago. But that might not be what you want to know, okay? We did that. We looked at the movie, and we were we didn't feel like we had advanced our knowledge. Okay? So we started thinking about, well, what do we actually want to know if we're trying to image this anticline? And well, if what we want to know is the height of the anticline, that is very well constrained. Okay? They all look like the same kind of fram. Okay? But what happens from model to model is the anticlines move up and down. Okay? They also move back and forth a fair amount, but they mostly move up and down. Okay? And so you can see the depth is very poorly constrained by our data set. Okay? So again, if that's what we want to constrain, we need to use different data. Okay, so this is my last example. So in this case, what we're trying to do is we're trying to fill in missing data. And this might not look like data to you. It looks like bullseye. The reason that it looks funny is it's seismic data in the frequency domain. And we are plotting source position on the x-axis and receiver position on the y-axis, okay? And so that's why it looks like this kind of expanding bullseye. So this is the fully sampled data, and we would like to fill in the data, and we would like to have an estimate of the uncertainty in the filled in data. And in this case, we actually want a point-by-point measure of the uncertainty across our entire data set, because we want to use this as a weight when we do full waveframe inversion later, okay? Because if I start from this data set, I want to downweight sort of the data in here because it's a big gap, okay? And so the data that I put in here is all interpolated, okay? And so I would like to tell my inversion algorithm, use those data, but maybe not. So I want a covariance matrix in that case, and I want the whole thing to a degree. I want the whole diagonal anyway, okay? And so in this case, we actually used a variational inference method called normalizing flows, where we then estimate this kind of point-wise standard deviation, okay? Because we have a different question. We really want those weights. And so we're going to learn those weights. Okay? So, to kind of wrap up, this quote actually came up last night at dinner time. So there are known unknowns and unknown unknowns. And what I want you to think about as you set up your inverse problems is to try and think through what all of those unknowns are and how they're going to affect the final result. And how the uncertainties in your data, the uncertainties in your model, etc., affect your final result is something that you should be thinking about when you set up your problem. And what question you want to answer is something you should be thinking about when you set up your problem, so that you can set up your problem with the right set of tools to answer the questions that you really are trying to answer as you solve your inverse problem. So that's all I have to say, and I'm happy to answer questions either now or later.